have mentioned in my previous lectures that different levels of material structure exist. So in the first level is so-called atomic structure. So in this lecture we will discuss some very basics of the atomic structure of different materials and the corresponding interatomic bonding which can exist based on the different atomic structures, and how these different types of interatomic bonding define the material structure. That's the main idea of the lecture. So let's start with history. So you remember maybe from your high school that Democritus, the very famous Greek scientist, more than 2,000 years ago suggests the idea of the atom, which means indivisible species from which all materials have been formed. That was his, I want to say, the genius idea, and based on the analysis of this information which you can see on the screen, that more than 2,000 years nobody can suggest anything better to describe the surrounding bodies, if you want. Only in the beginning of the 20th century, so based on the, I want to say, unique experimental data, so the new so-called Rutherford-Chadwick atom model was suggested and supported by very precise, I want to say, information, and we will briefly refresh our mind on this model on the next slide. So, however, it was a lot of problems with this model at the very end, which partially was covered by so-called classical quantum mechanical model suggested by Niels Bohr, and then the quantum revolution, the new quantum mechanical model of atoms has been built, and everybody are using this model for now. So now you can see on this slide the TEM, transmission electron microscopy images of the atoms in the different materials. Why I just decided to show you this information on this slide, for the reason that one more issue will be important in this course. We will also overview different experimental approaches which allows us to see deeper the different levels of material and allows us deeper understanding of the correlations between the material structures and their properties. That's why the electron microscopy will be one of the topic which we will discuss in future. So the results, the summary, if you want, of the Rutherford-Chadwick planetary model of the atom, you can see on the screen now. And pretty easy sounds for us now, but it was not easy, believe me, let's say at the beginning of the previous century. We know that the atom is pretty complicated structure, so it consists of nucleus, specifically of the positively charged protons and neutral particles, which are neutrons. So just reminding that there was about 15 years margin between the discovery of protons and neutrons. Neutrons was discovered in 1926 by Chadwick, and protons in 1911 by Rutherford. So that's why this model has this name, Rutherford-Chadwick model. So beautiful model. So we have a lot of electrons which are orbiting this nucleus, and the mass of electrons, as you know, much less than the mass of the protons and neutrons, and protons are charged positively while electrons are charged negatively. In general, in total, in the equilibrium condition, atom is neutral, and the charge actually of protons and electrons also has been measured, and so that was this beautiful model. And everything was okay unless one obstacle. And this screen demonstrates briefly this obstacle. Idea is very simple. So if you do have electron orbiting, let's say, the proton, which the case which we do have in the hydrogen atom, so because it's orbiting the atom, so it's moving with acceleration. And based on the Maxwell theory, Maxwell equation if you want, then that if particle is moving with acceleration, it should emit photons. Because of that, it should lose energy, and because of that, at some point, so all matters which we have around us should collapse. Indeed, calculations showed that collision between the electron and nucleus should happen in a small fraction of a second after the beginning of the existence of this material. So why in this case all materials around us so stable? So in order to resolve this obstacle, so genius idea should be considered by Max Planck. And I hope that you have heard about this idea of energy quantization. So Max Planck suggests that light actually comes only in the package or quanta of energy, and also he found that this energy is proportional to the frequency of the photons. So that's why we do have now the direct relation between the photon energy and so its frequency through the famous Planck constant. So this idea was used by Max Bohr, which in 1913 formulated the, if you want, the postulates for the new atomic model. And this postulate you can see on this screen. So first of all, he just suggested that there is no any emission of photons for the electrons which are moving along the allowed orbits. Good idea. Now the question is, what does it mean, allowed orbits? And here Bohr used the idea of quantization, and he said that these orbits are the orbits on which the angular moment of electron is equal to the number of Planck's constant. You remember this constant from the previous screen, right? So, however, we know that each matter may emit, may radiate. And the third Bohr postulate is the following, that indeed, when electron jumps from one stationary allowed orbit to another, then only it's emitted in energy, and the energy of photons emitted, again, is proportional to the Max constant. That was the brilliant idea. It's intermediate, of course, but brilliant idea which allowed actually precisely to calculate the emission spectrum of hydrogen. So indeed, a lot of experimental data exist at that time about the emission spectrum of hydrogen, and everybody was so excited and surprised actually that very simple calculation which involved the postulates, Bohr postulates, allows precisely calculate the frequency of photons emitted by hydrogen atom, which almost 100% fits whatever it was observed experimentally. So, however, or unfortunately, so this model worked greatly only for hydrogen and cannot explain the behavior of other, if you want to say, atoms. So now we have to make a huge jump ahead, and the work of many scientists, some of them are shown on this screen, so were used in order to introduce now not only one quantum numbers which define the quantization of energy, which it was suggested by Bohr, but 4 quantum numbers which are shown on this slide. And it was postulated at the very end that these 4 quantum numbers precisely defined the set of the 4 quantum, defines the electron structure of any element which is known for us today. So that's why the quantum theory allows us precisely calculate, if you want, or precisely describe the electron structure of each element, and why it is important for us, the electron structure of elements allow us predict the type of bonds between these elements during the synthesis of production of any type of materials. So that's why the atomic level of bonding defines the many of material properties which I mentioned in our previous lecture. So let us go a little bit in more details in order you can feel these correlations between the electron structure of elements, which is described by quantum physics theory, and the type of bonding in materials. Different type of bondings correspond to different types of materials. Just refresh your mind: metals, ceramics, and polymers. So thus we know that the set of 4 quantum numbers precisely describe the electronic structure of any considered elements. If you want to know a little bit in more details about this kind of electron structure classification, you may go to the full lecture number 3, which is related to this video course, where you will find the physical description of each of quantum numbers. You will figure out how you can derive these quantum numbers, and you will know a little bit more about the history of the discovery of these quantum numbers. For us today is important that indeed set of 4 quantum numbers defines the electron structure of each element, and in turn the electron structure of the elements defines the type of the bonding which you can expect when you start the processing or synthesis of any kind of complicated materials. So now, in order to feel better how the set of electron structure or electron structure of materials defines their properties, let's spend 2 more slides talking about the quantum numbers. So on this screen, pretty complicated survey of elements which describe with the help of these quantum numbers. And if you just make a columns of elements with the similar valence electrons, and I hope that everybody knows what does it mean valence electrons, then, oh surprise, you will come to the famous periodic table of elements, which was suggested by Dmitry Mendeleev in the 19th century, when he had no any clue about the existence of the quantum numbers. So now we are on the periodic table of elements, and if you remember, all elements are located now based on this the electron structure. Analysis of the elemental table allows us predict the type of the bonding which one may expect when synthesized material. Let us take such example as, let's say, magnesium oxide ceramic. You can see that magnesium is located on the left side of periodic table, which means that it has only few electrons, only few valence electrons. While oxygen is located on the right side of periodic table, it means that it has number of electrons close but not equal to 8. So in this case, it's easy to imagine that magnesium will easy to give electron to oxygen, and oxygen will accept this electron. And in this case now we do have 2 ions, the positively charged magnesium and negatively charged oxygen, which will interact with each other through the Coulomb type of interaction. And Coulomb type of interaction, if you know, is extremely strong. So this ion bonding type So because it occurs through the Coulomb interaction, and we know now why. So provides actually indeed high hardness of material, extremely high melting point, and unfortunately brittleness of the material, and also relatively low electron and thermal conductivity. So other example, if we try to create other ceramics, let's say silicon carbide ceramics, widely used, let's say, in the aerospace application, because it has outstanding chemical durability and extremely high thermal stability. So you can see that this ceramic consists of silicon and carbon. Both these elements are located even in the same column, 4A column of periodic table. It means that they do have relatively similar, I want to say, the electron structures. In this case, we are talking about covalent bonding, so which actually can be extremely strong, as in the case of silicon carbide, or relatively weak, as in the case, let's say, of different gases such as hydrogen, oxygen, and so on and so forth. So that's what we are talking. In this case, there is no any exchange of electrons. In this case, two atoms share in some sense their electrons and providing this type of structure. And so how do they share? That defines the case if we have a strong bonds or we do have the weak bonds. Indeed. So on this slide, on this screen, you can see that so this type of structure is characterized such material as diamond, which is which has extremely high hardness, very high melting point, and high brittleness. On the other hand, so let's say silicon also has this type of bond, very well known, let's say dielectric, which has a relatively low hardness, low melting point, and also brittleness. So finally, we can talk about metallic bonding. So, and all metals are located somewhere in the middle of the periodic table. So in this case, we do have the other way of bonding, where the sea of electrons, which doesn't belong to any specific pair, exists and actually defines all known metallic properties, such as high electron and thermal conductivity, high strength and ductility, magnetic properties, and wide range of melting points from -40 C to almost, let's say, 3.5 thousand Celsius. So finally, we have to talk about this secondary bonding. Otherwise, we have no chance to describe polymers. Secondary bonding arises from the interaction between dipoles, not between ions as we do have in the case of ion bonding, but between dipoles, and because of that, this physical type of bonding is relatively weak and is on the order of 0.1 electron volts per atom. Again, ion bonding is on the order of 1 electron volts per atom. So in the case of secondary van der Waals bonding, we do have much weaker interaction. However, this interaction plays a very important role in the building of the material, especially in the case of polymers. Indeed, polymers, as we mentioned in our first lecture, is the material which involves very long chains of macromolecules. And between these MERS, if you want, so extremely strong covalent bonds plays important role. However, between the chains, we do have typically relatively weak secondary bonding, and this weak link at the very end defines the considered property such as low melting point, low strength, if you want, and high elasticity. So now you know that based on the electron structure of each elements which you use for building of your material, you can predict the type of bonding, you can expect the type of bonding between these elements. And the different type of bonding, specifically ionic, covalent, metallic, and secondary, they defined the corresponding property of the material. Indeed, in general, you have to understand that ionic and covalent bonds are very strong, as well as metal bonds, and secondary bonds are relatively weak, 10 times weaker than the upper ones. And however, this bonding also has some other structural specifics. Ionic bonds is non-directional bonds, while covalent bonds is directional bonds. That's why, this also, and we will know that, we will discuss it, also make some influence on the material properties. But typically, what we have to expect, extremely high, let's say, energy, remember 1 electron volts per atom of ionic and covalent bonds, which are characteristic for ceramics, provides such property as large melting point, large elastic modulus, relatively small coefficient of thermal expansion. In the case of metals, we can expect moderate melting points, moderate elastic modulus, a moderate coefficient of thermal expansion. So in summary, we can see that different primarily atomic bonds correspond to different type of materials. For ceramics, typically we do have ionic and covalent bonds, which we know that very strong one. That's why we do have high melting points, high strength, high elastic modulus, and other property. But on the other hand, because we do have directional covalent bonds, we do have high brittleness of these materials. In the case of metals, which do have metallic bonding, remember the sea of electrons, we can expect extremely high electrical and thermal conductivities and relatively high melting points and elastic modulus, because the strengths of the metallic bonds are slightly just smaller than for the ionic and covalent bonds. Finally, for polymers, while we do have covalent strong bonds between the mers, the relatively weak secondary bonds, which is on the order of the 0.1 electron volts per atoms, somehow suggest that in this case we have to have small melting points, small all kind of mechanical property, including elastic modulus. However, we have to expect very high elasticity. Thank you so much for your attention.